Let's look at the relationship between the equilibrium constant and temperature. In order to do this, we'll need to remember the equation for calculating delta G, and we'll need the equation that we just discussed that relates the equilibrium constant to delta G. Now, let's see what happens when we start substituting in delta H minus T delta S into this equation here. So let's write that down here. Ln of K. And that would equal negative delta G over RT. But I'm going to start substituting in this for delta G. So that means I should have that equal to negative delta H over RT, and then plus, because that's a negative there and a negative here, so that's going to make this plus. And then this is T delta S over RT. So my temperatures are going to cancel, and I can simplify this down to negative delta H over R times 1 over temperature. I'm going to pull this temperature out just for clarity in a minute. And then plus delta S over R. Now, you probably see where this is going. Let's write this without this intermediate stuff in here. We have Ln of K equal to something that looks like the slope of a line. Something that looks like an x value here, 1 over temperature, plus, and then right here, this looks like the intercept. So, what is the usefulness of this equation? Well, we can, at various temperatures, measure the equilibrium constant. So, it's possible to measure equilibrium constants, and so we just do that experiment for several different temperatures and record the values. Then we'll plot the natural log of K on the y-axis, and then on the x-axis we'll plot 1 over temperature, making sure that we have temperature in kelvins. And then we should get a straight line. Something like this. Now, the usefulness of this line is that from this we fit the data, and then we can find out, here's the slope. It's negative delta H over R. So we can get the enthalpy of the reaction from the slope. And then from the intercept, we can get the entropy information. Now we'll just have to multiply both of those things by R, and in this case we'll have to change the sign, but then we can determine those important thermodynamic values from that. And then from there, if we wanted to, we could calculate what the value of the equilibrium constant is at various temperatures, keeping in mind that if we go too far away from the data that we've measured, we may get into some secondary effects because delta G or delta H and delta S have small temperature dependence to them. and that will creep in if we wildly change the temperature. But for a small change in temperature, this is very useful in order to determine a new equilibrium constant, or again, getting those important thermodynamic values of delta H and delta S out of the data.